Right, hello, this is the review that from office hours covering the Unit 5 Module 1a homework. That is the content that will be on Pop Quiz 1 and our Unit 5 Module 1 homework that's due on Sunday. Right, so we're going to go through several of the ideas that are on the homework, and some of them were brought up in class. And so let's take a look at them in detail. Okay, so we were asked to rank the energetic stability of these three molecules, and you'll be asked to do this in the homework too. So let's take a look at what we mean by energetic stability. So this is a ranking of potential energy. The most stable is the lowest potential energy. The least stable is the highest potential energy. And today in class, we rank this based on polarity. So when we look at these three molecules and the bonds associated with these molecules, we have a nonpolar bond, which is HH. We have a slightly polar bond, which is CH. And then we have a very polar bond, OH. So the most stable would be the most polar under this model, and we would pick OH to be the most stable. If we were to want to rank these graphically based on potential energy, it would look like this. The HH bond is here, it's nonpolar, and since it's closest to zero, has the highest potential energy, it requires the least amount of energy to separate the HH. The most stable would be lower potential energy, right? And it requires more energy to separate the OH bond, and then CH is somewhere in the middle. So the least polar bond, most polar bond, and this is how we would rank them graphically. Right, so our current model is based on polarity, and we would rank these substances this way. Okay, so here we have which of the bonds are lower in potential energy than the CN. So here's the model we had, which was that first we need to determine the polarity. And the polarity of the carbon-nitrogen bond is based on the absolute difference between the electronegativities of the carbon atom and the electronegativities of the nitrogen atom. So chi, the Greek letter chi, stands for electronegativity, and it was used in 151 as a stability index. So the greater the number is, the more stable, the lower the potential energy is of that atom. So polarity for CN. Okay, so once we have the polarity, then what we'll do is we will take the negative of the polarity and call that potential energy. So what we're asking here is, for one, when it says what is the lowest potential energy, or which one is the lower potential energy than CN, we're saying which one is really more polar, because when you take the negative value, that would have a lower potential energy. So let's look at the numbers. All right, so carbon-nitrogen is here, has a certain polarity, right? 2.5 minus 3.0. Remember, we're looking at absolute values here. The polarity here is 0.5. So the polar bond here is 0.5. Now what we're going to do to calculate the potential energy is take the negative value of it, and we get minus 0.5. So what we're going to do is graph this. So we put minus 0.5 here for the CN bond. Now we go through the list. CO, well, its polarity now is different. It's 2.5 minus 3.5, which is 1.0. We can calculate the potential energy to be now minus 1. CF, we can do the same thing. 2.5 minus 4, 1.5. Its potential energy is minus 1.5. And then OH is 2.1 minus 3.5, and we get 1.4. So if we add these to our graph, what we see is all the other three bonds are all lower in potential energy. They're all more stable than our CN bond, and this is how we would rank the potential energy of these different bonds. So the current answer would be all of them, right? They are all more stable because they have lower potential energy than the CN bond. Okay, so now let's go into the homework. So those were two questions that came up in class, and now we want to know, like, how do we apply the ideas from the class into the homework questions? All right, so we're being asked to rank potential energy here for these molecules. So the first thing we want to do is we want to put in our electronegativity model. So if I take the periodic table, the atoms of the periodic table that's being asked about, we want to keep in mind our electronegativity trends. Electronegativity trends are that electronegativity increases as you go left to right on the periodic table, and electronegativity goes down as you go down the column. Okay, so let's take a look. These are, so we want to find out what are the weakest, highest potential energy bonds, and then the strongest, lowest potential energy bonds. Okay, so when we look at this, the most electronegative element here is going to be fluorine. It's the highest and farthest to the right. So HF would be the strongest, most polar bond. Now, if we are going just in the second column, HO would be a little less stable than HF, so it's higher up in potential energy. But then what we see as we go down the column, it would then go HS and then selenium. So now selenium is going to be the least stable. It has the lowest difference in electronegativity compared to hydrogen. And these are all being compared to hydrogen, right? So they're all kind of the same. So really what we're saying is we're just really ranking potential, the chi's for each of the elements, since hydrogen is the same. So this would be our ranking from the most negative potential energy at the bottom, HF, and then selenium, H selenium bond would be the weakest or highest potential energy. Of course, that also means that we would predict the HF to have the shortest bond, and then the HSE bond to be the longest. All right, this is another question from the homework that has you rank the amount of energy released when these bonds are formed. Okay, so let's take a look at the single bond, double bond, triple bond model. So this is coming from Chemistry 151. This has to do with delocalization of bonding electrons. So the more electrons that are delocalized, you're going to have a stronger bond. So the single bond only has 2 electrons delocalized, so the smallest number of delocalized electrons of 2. Triple bond has the greatest number of delocalized electrons, total of 6, which makes it stronger and shorter. So this is the stronger and shorter. So the highest potential energy is in the single bond with the longest bond. Triple bond is the shortest because it's stronger and it has more delocalized electrons as 6. Okay, so that means we can now go into the problem and say, okay, well, the amount of energy released, the greatest amount of energy released is the one that has the lowest potential energy. The greatest amount of energy required is also the one with the lowest potential energy. So the most energy released is the most stable. That would be A, right? A is the most stable. So just keep in mind there's a couple versions of this problem, but energy is required to break a bond. The greatest amount of energy required to break a bond is the triple bond, but the amount of energy released to break a bond is incorrect, right? Because you release energy when formed, but you required energy to break. All right, so there's several problems in the homework that look like this. So we're going to go through our sign convention and our, so let's just make sure, oops, that this is really about exothermic reactions. Okay, not that. Okay. Right, so which reactions are exothermic? That's what we want to do. So let's take a look at our model. So remember, our model for exothermic reactions look like this. Potential energy, reactants and products, right? That's our energy diagram. And we have high potential energy reactants going to low potential energy products. And based on our energy analysis, we identified elements as being the highest potential energy. So remember, changes in potential energy going from high to low result in a negative number. The negative number is what we call exothermic. So this is going to occur. So what we're going to do first is identify all the elements in the reactions. It's going to help us. So every time an element is a reactant, we know we have the exothermic model. So we can write the elements up there. They're high, compounds are low. The change in potential energy, which we are now calling delta H, or change in enthalpy, is now negative. In B, exothermic, right? So if it's negative, it's exothermic. In B, we see that our products have the element, and so we're going from low potential energy compound up to high potential energy products, elements. In that case, the change is going from low to high. That change is positive. Whoops, sorry. That change is positive. And then when we look at C, C is the same as A. We have reactants that have high potential energy. That gives us a change going from high to low. High to low is a negative change that is defined as exothermic. Okay, so that's how we would use these ideas to apply to our model, in which the weakest bonds, right, oops, sorry, that's not right. The weakest bonds or the highest potential energy are nonpolar long bonds, which we have called the elemental form, right? The elemental form. And that's what we've been applying here. And you want to feel comfortable applying this model to reactions, which we're going to do in the next problem. All right, so at the very end of class, but this is also a problem from our homework, what we want to know is which of these are energetically favored. And so what we want to do is unpack this word, because what we mean by that energetically favored is we're saying is which one of these reactions favor the production of products. That's what we mean by energetically favored. So the products are at low potential energy. That's what we mean by favored. And it's just part of the language. Chemists are, obsessed with products, and so we want to know which one of these reactions at equilibrium will have the most products made. All right, so what we're going to do is take a look at some techniques to identify that. First, our general model is to identify elements and assign them as high potential energy. So let's do that. In A, it's O2. How do we know it's an element? Well, and AA bonds and AB bonds. So remember, what we're going to do is we're looking for the molecule. If it only has one type of atom, it must be an element. All right, so here we see that there's 3 AB substances and 1 AA bond. We have CH bonds here, OO bonds, CO bonds, and OH bonds. Now, we don't have to know too much about the molecule, only we do know that there's different types of atoms, which means different types of bonds. So we'll call that a generic AB. All right, so let's, on B, item B, we see that the element is in the products. So in that case, what we see, we can start to assign our Right? Every place we have a circle, all I'm doing is circling the elements. We assign that as high potential energy. So you can see here, I put the circles, right? All circles mean high potential energy. Circle are elements. They only contain one element. In this case, AS is an element. H2 is an element. O2 is an element. Aluminum's Al solid is aluminum. B solid is an element. And Fe solid is a element. These are all high potential energy substances. So they're all high potential energy. If they're reactants, then we know we have an exothermic reaction because we will be in the high-low method, high-low model for exothermic. I'm going to change that. If the high potential energy, right, if the high potential energy is a product, then we are working with the endothermic model. So all we really need to do is find out where those circles go, right? If the circle, every time we have a circle, we assign it as high. If it goes, and so in our model, so we go high to low, RP. This change is going to be negative exothermic. If it's low to high, remember our circle was there, circle's here. That's our element. That change is positive. We call that endothermic. So that's our fundamental model for assigning whether a reaction is endothermic or exothermic. All right, so that is all the content that is on our quiz. Ionic compounds, the energetics of our ionic compounds will be covered next week, along with changes in configurations and entropy. Good luck, everyone.